Hi there, this is Math 8, Unit 5, and we're looking at Lesson 5 called More Graphs of Functions. We're looking at more graphs of functions today. And so we're going to be learning how to interpret graphs and functions, meaning let's talk about what do we see happening within the graph. So you began first off today with this which one doesn't belong, with a picture of 4 different graphs. And you had a little conversation in class about which one probably doesn't belong for different reasons. And there's, again, no real right or wrong answer here. It's just a question of what do you see and which one do you think doesn't match or fit with the other ones. And so you had a little discussion in class there. So for example, if you looked at all these, for example here, letter A, we could say this one here seems to touch the x-axis, where the other ones aren't touching the x-axis at all, so maybe that makes it different. In the same way over here, this one touches the y, but so does that one. We talked the other day in our lesson about having kind of what we call the vertical line test, right? Where there's 2 points that go down this vertical line. So we would actually say that this one would not be a function just because of the way it is shaped there, right? You can't have 2 y values for 1 x value. Right, this is 2, you can't have a value here at 1 and another value at that 2. It's just not going to work out too well. All right, this one here, maybe it doesn't belong because you have, I'm not quite sure. Like this one seems a decrease, this one doesn't have any decreases. So, again, the idea is it's not straight. You get to decide what's there. This one's interesting because you don't have a straight line or continuous line. Instead, you have what are called discrete points, okay? Meaning that they're not connected there, where everything else seems to be connected. There's differences for each one, so which one doesn't belong is really up to your interpretation. So let's look at the next section. This next section shows a graph of temperature between noon, right, here's noon, 12 o'clock, and midnight in one day in a certain city. So we can see this temperature at noon is about here, and it tends to go up a little bit, and then it comes back down as it gets closer, further on in the evening there. So it's that gradual increase and decrease of temperature in one city. So in this problem, what it's asking us to do is answer a series of questions related to this graph itself. So first it asks, was it warmer at 3 p.m. or was it warmer at 9 o'clock p.m.? So to determine that, we're going to take a look at the time, which is here on the x-axis, and we're going to go up to 3 o'clock and put a point. We could put a point right there for where the temperature is at 3 o'clock, and we could put a point at 9 o'clock p.m. right there. And then we just need to make a determination. Well, which one has the higher temperature? And we would say this point here has a higher temperature, and we would say 9 o'clock is when it was warmer, at least compared between those two temperature points. Obviously it's warmer up here, but if we're just comparing those two, we would say it was warmer at that point there. Approximately when was the temperature the highest? So if we're looking for the highest temperature here, we're going to want to find the peak point in our graph, which is located right about there, and then just take a little line down here and kind of eyeball it and say, well, about when was that? And so it happens somewhere around there. So maybe you say that that is a little past 5:30, maybe it's 5:45, maybe it's 5:40. Again, it's an estimate somewhere between, you probably want to say that at least it's somewhere between 5:30 and 6 o'clock. It's in that range there, so pick some kind of time that goes between those 2 points, okay? Find another time the temperature was the same as it was at 4 o'clock. So to do this, we're going to take our little pin, we're going to make a point here at 4 o'clock, and then what we want to do is move across horizontally and find a spot where it's the same temperature. And so when we move that across there, we can see that right about there, somewhere at about, looking down, 8 o'clock, it was the same temperature as it was at 4 o'clock. So we could say about 8 o'clock. It's not exact, but it's close. It gets me pretty close there. Did the temperature change more between 1 and 3 or between 3 and 5? So we're looking for that temperature change in those two ranges there. So I look at 1 o'clock. At 1 o'clock, we're somewhere at about 50, well, hard to say. At 1 o'clock, p.m. At 1 o'clock, we are right here at 50.5 degrees. And at 3 o'clock, we say we're maybe at about 54.5 degrees. So that's going to be an increase from here to here, right? That increase right there, that's our increase amount. So how much are we moving up there to go from there to there? we can look at the vertical side and say, well, I go from here, I'm going to go up 1, 2, 3, 4. So that's about a 4-degree increase right there. When I look at what's happening from 3 to 5, 3 o'clock is here and 5 o'clock is here. And so if I kind of draw my line across there and say, well, how far up am I going vertically? I'm going up 1, 2, 3 and a bit, right? That's probably about a 3.5 degree change there. So at what point am I increasing more? We can see there's a greater vertical step here than there is there. And mathematically, 54.5 minus 50.5 is about plus 4 degrees compared to 3.5 degrees. So we would go with there was a greater change between 1 and 3 o'clock p.m. Does this graph show that temperature is a function of time, or time is a function of temperature? Now remember, when it comes to function, we're saying which one depends on which. In this case, our x-axis is time, right? So time is our independent variable, okay? And our dependent variable is going to be the temperature, and that's our dependent variable there. And as a result, we would say, in our case here, we would say that in our case, temperature is a function of time. And remember, the way we can kind of interpret that, if you're not kind of grasping it so far, is that what we always say is that our dependent is a function of our independent, or that the dependent depends on the independent, right? So temperature depends on the time. So the temperature we recorded depended upon the time of day in which the recording happened at. All right. Number 6 says, when the input for the function is 8, what is the output? What does it tell you about time and temperature? So when you put in 8, you ended up over here at 57 degrees. Okay, so 57 degrees. And all that tells us about time and temperature is this, that at 8 o'clock, the temperature was 57 degrees. That's all we can really say that it's telling us in this graph here. Okay, let's look at the next page. And this next one, a couple extra dots from my marker, sorry about that. We have this graph that shows the amount of garbage produced in the US each year. Okay, ranging from 1990 to the year 20, in this case here, 2013, which is where we stop right there. Questions are, did the amount of garbage increase or decrease between 1999 and 2000? So we need to come up here and find 1999. Here's 95, 96, 97, 98, 99, and here's 2000. So between these 2 points here, am I increasing or decreasing? Because I'm moving from here to here, moving up in terms of my amount of garbage, we would call this an increase to the amount of garbage in between those 2 years. Then I look at, did the amount of garbage increase or decrease between 2005 and 2009? So I look here at 2005 and I have 6, 7, 8, 9. So moving from this point to that point, because I'm going down in terms of my line there, we would consider that to be a decrease. Yes, it did increase momentarily for a year, but overall, the trend is that it's decreasing over time. Between 1991 and 1995, the garbage increased for 3 years, and then it decreased the 4th year. Describe how the amount of garbage changed in the years between 1995 and 2000. All right, so looking here at this point here, we're talking about this range of data from 95 to 2000. We can see that there was initially, looking here, a decrease the first year, right? That's our first thing. But from that point on, then it was an increase the remaining 4 years. Okay, so we see an increase the first year, or sorry, decrease the first year, and then an increase the following 4 years there on the graph. And that's the idea for 5, 3. Okay, for at least the number 1. Let's take a look at the next graph. This graph shows the percentage of garbage that was recycled between 1991 and 2013. Okay, so we see the percentage of garbage that's being recycled from here to here. Obviously, overall, we can see that the percent starts somewhere at 15, and we have a high point here close to 27. So we can see that garbage tends to be more recycled initially for the first 5 years or so. Then it slows down a little bit, and then gradually starts to increase some more, and there's been a slight decline over here. So just in terms of the percentage of recycled garbage, there's an increase, a slowdown, an increase, and then a decrease there. So when was this? When was everything increasing? Okay, so for the most part, we could say that from 1990, if we start here, this is all moving upwards, upwards, upwards until we get to this point right there. That's in the year 1996. So there's certainly an increase from the year 1991 to 1996. There's an increase in that point there. When we look here, we have a decrease, and we can see our next question real quick is a decrease. So let's just jot this in here. There's a decrease from 1996 until 1997. There's a decrease there. From this point, 1997, I don't know if that's a decrease or a change. It doesn't really seem to change at all. We could probably say nothing happened there. It stayed the same. But from this point forward, we can see that in 1997, 1998, 98, we're moving up, 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 and then still maybe slightly up, up, slightly, slightly up. And there tends to be a steady kind of increase there during those years there from 1998 until maybe, we could probably say, I mean, it depends what we want to say. If this is going to be like a straight across no change, let's call this a no change. How about that? We'll call these a no change there. So we could say it increases from 1998 to this point here, which is 2001. We could say that then there's a no change there, but it increases from 2002 to 3, 4, 5, 6, 7. Okay, and I'm just counting up. This is 5, 2005, 6, 7. No change there. This is 8. And so I get 2008 then to 9, 2010, 2011 there. We definitely have a decrease though from, and we could maybe say that's a decrease. If we wanted to, we could call that a decrease or the same. I call it the same for now. Let's go ahead and just use this as our other decrease there. And that's going to be happening from 2011 to 2013. Again, this is just my estimates based upon what I'm seeing. It's not accurate because these points here don't have, the grid lines that tell me exactly where things are at. So tell the story of change in the percentage of garbage produced in the U.S. over this period of time. So what you might write down or might say or in your discussion, or you did today, was that the percent of garbage recycled gradually increased from 1991 to about 2011. I mean, while it had some slight dips, overall, the garbage was increasing in how much it was recycled from 1991 to 2011, right? There seems to be a general increase in the percent recycled. But we can also see that now, in terms of 2011, 2013, the last 3 years there seems to be a decrease in the percent recycled. And that's just based upon what we see visually in the graphs there. All right, so let's take a look at your summary before we jump into tonight's homework. It says here's a graph showing temperature in a town as a function of time. So this is the temperature is a function of time. Remember, our time is our independent, and our temperature in this case here is our dependent, meaning the temperature that's recorded depends on the time at which that happened. This is our x, this becomes our y. All right, so the graph of a function tells us what is happening in the context of the function represents. In this example, the temperature starts out at 60 degrees Fahrenheit at 8 o'clock p.m. It decreases during the night, reaches a low 8 hours after 8 p.m. or 4 o'clock a.m. Then it starts to increase again. Okay, so that is just an example of a graph showing a function happening with weather. Let's take a look at your homework tonight. So take a moment to do your homework, and then let's see how you did. All right. First of all, with tonight's homework, we are given several statements here, numbers 1 through 6, that correspond to the graphs over here. This is the interesting problem, and I know when I first was working on it, you do need to look at each of the pictures to get a feel for what they might be showing. Then as you read these, you might find that you can figure out what goes with what, and you get them a little, different order as you go along. Like it might be easier to figure out number 4 before you do number 1, based upon what you see happening. When I look at these graphs, I can see that I have, a gradual increase there. Here for B, I'm going up and reaching a peak and then coming back down. C seems to be linear. D is linear, but it's starting at a different point there, right? It's not starting at the same point as sorry, we're not lead here. It's not starting at the origin, which is interesting. That's not starting at the origin there. E is decreasing, so that's different. And F seems to go up, but then slow down there. So let's take a look at what we have here. First of all, we see that we have, in all the statements, the function inputs the age of an oak tree, A, and outputs a prediction of the height of the tree, H. So we're going to begin with the input of age of an oak tree, okay? So the age of an oak tree, A, is our input on the first one. The next one says the function inputs the edge length. So we have edge length is E. Here the input the distance. This one inputs the height of a triangle. This one inputs the time of day. And this one inputs the time of day as well. Those inputs are all going to be, if you remember, our independent variable or our x values here, right? So these are our x values, our independent variables. So looking for the age of a tree, the edge length, distance traveled, height of a triangle, and so on. The other information looking for are the output, right? In this case here, the output is the height of a tree. Here we have the volume V. Here we have the fuel that's left. Here we have the area, temperature, and the number of cars washed. Those become our dependent variables, or our y variables here, like so. Okay, so let's take a look at what the things are asking. I have an age of an oak tree. So age is going to be continual. It's going to keep on going, right? It's independent. It just grows older with time. But the height of a tree is going to change depending upon how long it's been growing. Now we can look at a tree like this, for example. This would be like starting from nothing and it gets really tall, but notice as time goes on, it just kind of stops growing there. But is a tree going to continually grow, or will it eventually reach a point where it doesn't get much taller, or it starts to slow down its growth? Here a tree could grow and then shrink. That doesn't make sense. Do you think a tree grows like proportionally, like the same amount every year? Probably not. Does a tree start off and doesn't grow at all for the first couple of years? Hard to say there. If you were to count the seed time, maybe, but there's still some growth. A tree is not going to start here and shrink. And this one has something that could be growing but then slowing down over time. This one to me makes the most sense to be the tree. So I would label this as A, and I'd label this as H. And we would say number 1 seems to match graph letter F, because the height of a tree is going to continually grow, but then it's going to slow down how tall it gets with time. Okay? The function, number 2, inputs the edge length of a cube and outputs the volume. Okay? Now volume we talked about before, because it's cube, volume is not going to be linear. It's not going to be like a one-to-one type of thing. It's going to increase faster the longer the edge length is going to be. And so in our case here, because it's not linear, it's not going to be those ones there. Volume is not decreasing, and volume isn't going to show variance. So we'd go with A for number 2. Okay, and so our edge length here is E, and then our volume is V on this one there. Okay, and so you can label it with the letters or the words, but I'm doing the letters because they're giving me those letters there. Okay. All right, number 3, the function inputs the distance traveled, D, and predicts the amount of fuel left in the tank. Notice how it says the amount of fuel left. That gives me a clue that this is going to be a decreasing type of function. I'm going to start off with something and I'm going to be decreasing. The only one of these that's decreasing, well, B has some decrease, but this would be like I have a little bit of fuel and as I drive I get more fuel and then I start to lose fuel. Doesn't make sense. The one that's the best decrease is here, E, which would be with distance traveled D, and the fuel left in the tank F, showing I start with some and I start to run out the further along I go. So number 3 seems to match with E. The function inputs the height h of a triangle with base 12 and outputs the area A. Okay, so we have the height of something with a base 12, and off we go. Okay, so let's take, for example, if the height was 0, 0 times 12 is 0, so I would actually start at the origin, wouldn't I? So this is going to be, area is much more linear, it's going to be a line, whereas volume, we said before, is not. Volume is going to have that curved shape there. So the best one for our area is going to be C. So we're going to make our height our x value and our area our y value. A couple more left here. This function puts the time of day and the temperature. All right, so looking here, is time of day going to be, is temperature going to be constantly just increasing, like it's going forever and ever, or is temperature going to show some variance? I'm probably going to go with temperature show some variance, right? Maybe this is the morning, and as the day goes on, it gets hotter till you get to mid-afternoon, and then it starts to cool off in the evening. That makes the most sense to me. So we're going to call this T for time of day, and this will be a capital T for the actual temperature there. Which leaves us then finally with D as our last choice for the time of day and the number of car washes, number of cars washed at the car wash C. Why? Could you have nothing for a while? Maybe you didn't get any people to come get the car washed for a while, and suddenly, you know, a little bit into the day, people finally start to come. That works there. Let's look at number 2. The solution to a system of equations is 6, -3. Choose 2 equations that might make up the system. So remember, a system of equations means that if I put these variables, or these numbers, sorry, the coordinates, into the equation, I'm going to get the solution. So if I plug in the 6 in the x, I end up with the -3 there. So let's see how this works here. This first one, I have -3 times 6 plus 6. And I want to try to get to -3 as my answer for y. So that becomes -3 times 6 is -18 plus 6, which equals a -12. That's not -3, so we would say no for A. The next one, we have 2 times the 6 minus 9. 2 times 6 is 12, minus 9 equals a +3. Well, I want a -3, so that is also not going to work. For choice C, we have -5 times 6 plus 27. -5 times 6 is -30 plus 27. A -30 plus a +27 equals a -3, right? There are more negatives than there are positives, so I have -3 there. That's going to work just fine. Next, I have 2 times 6 minus 15. Well, 2 times 6 is 12 minus 15. It's going to leave me with a -3. So that's correct there. And then finally E, -4 times 6 plus 27 is going to be a -24 plus 27. That equals a +3, also not going to work. So our 2 solutions to a system of equations, or the 2 equations that make up that solution, of that system, are going to be C and D based upon the information we have there. All right, let's take a look at the next page. Got a long problem here. All right. It says that a car is traveling on a small highway and it's either going 55 miles per hour or 35 miles per hour. So it's changing its rate, its speed, depending on where it's at, depending on the speed limits, until it reaches the destination 200 miles away. So that's how far it's going, is 200 miles away. Letting X represent the amount of time in hours the car is going 55 miles per hour, and Y be the time is going 35 miles per hour, and the equation is this. So 55x plus 35y equals 200. All right, so now we have a series of 3 questions. If the car spends 2.5 hours going 35 miles per hour, right? If this is the 35 mile per hour one, so this becomes our y. How long does it take to, how long does it spend going 55? So our y value is given. We want to solve for x, okay? Over here, we see that it goes 3 hours at 55 miles per hour. That's the x. So in this case here, because we're trying to find the 35, we're going to solve for y, okay? And over here, we have no time going 35, okay? So we have 0. So again, we're going to solve for In this case here, we're solving for the x, okay? Because they're giving us the y value there, okay? So now what I want to do is actually do 3 different problems. So here's A, we'll do A first. A, I'm going to use 55x plus 35y equals 200, and we're going to use 2.5 in the place of y. So we'll have 55x plus 35 times 2.5 equals 200, and now we just have to work this out to solve for x. So to do that, I'm going to multiply those together first of all. So I still have 55x. This becomes plus, in this case here, we have 35 times 2.5, which is going to be 87.5 equals 200. Okay. Now I want to get the 55x by itself on one side. So to do that, I'm going to subtract 87.5 from this side and this side. That makes that eliminated there, and I'm left with 200 minus 87.5, right? Which is going to be 112.5. Now I'm going to divide both sides by 55, and x is going to equal, in my case here I got 2.045, and we would probably round that up to the nearest hundredth there, so we would say 2.05. So for how long does it spend going 55 miles an hour? It's a little bit over 2 hours, 2.05 hours is what we would say for that one right there. A little bit strange, I know, but that does work, and that's what you end up with there. Okay. Okay, for B, we use the same equation, 55x plus 35y equals 200, and we're going to plug the 3 in the place of x. So we have 55 times 3 plus 35y equals 200. 55 times 3 is 165 plus 35y equals 200. I'll subtract 165 from both sides. So I'm left with 35y equals, in this case here, 35. Divide both sides by 35, so that y equals 35 divided by 35, 1. So if it drives for 3 hours going 55 miles an hour, it will only drive for 1 hour going 35 miles per hour. And then finally, our last one, it has no time going 35 miles an hour, which means I have 55x plus 35y equals 200, and no time means a 0, right? So this becomes 55x plus 35 times 0 equals 200, or just simply 55x equals 200 because that goes away. So I divide both sides by 55, and x is going to be equal to 3.636. If I round to the nearest hundredth, which we usually do, we would say 3.64. 3.64 hours is about how long that would take to go 0. All right, so those are my answers for A, B, and C for number 3. The next one says, the graph represents an object that is shot upwards from a tower and then falls to the ground. The independent variable is time in seconds. The dependent is the height of the object above the ground in meters. Let's take a look at the graph here on the next page. We can see here that in this case, we have the object which starts at the tower, and the tower must start here at about 10 meters is where it's going to start. We're not starting at 0, we're in the tower somewhere, right? So here's our tower. There's our nice little tower. All right, and we're going to go up and then come back down and hit the ground over here. So how tall is the tower from which the object was shot? To determine that, we look and see, well, where did it start from? It started here at 10 meters. Okay, and that's how tall the tower was. When did the object hit the ground? Well, the ground's going to be when it's equal to 0, and that hits the ground right here at about, by seconds, 1, 2, 3, 4, 5, 6, about 6 seconds. A little more, but that's okay. We're just estimating here. Okay, and then finally, estimate the greatest height of the object reached and the time it took to get to that height. Indicate the situation on the graph. So we're going to look for the greatest height. which is probably somewhere, it looks like about here, is our greatest height. So what is that greatest height? Well, we can look across and see here on this point, like about where is that? We're counting by 5, so this is 90, 95. It's between 90 and 95, so we'd probably say that's about 92.5 meters in the air. And when did that happen? Again, we come down this way and look for our time, or our x value, and we can see it's about, this is 2 seconds, 3 seconds, this is 2.5. So we're between 2.5 and 3, so maybe here at about 2.75 seconds is about when that reached the height. So in about 2.75 seconds, it reached its greatest height, which was 92.5 meters. That's seconds, that's meters, and that's how you would write that down there. And that is really it for today's lesson. We'll see you next time.